We had an interesting chat with some of you after the lecture, at the end of the lecture yesterday. And I was talking about this perpetual motion fan that can be found on YouTube, where some people claim that you can have a fan that is going on forever. Okay? Some of these are hoax, but some of them are not. Okay? So the higher the number of people who see these YouTube segments, the highest the likelihood of that thing being hoax. But don't dismiss the concept or the possibility of what appears to be generating energy, what appears, I underline this, what appears to be generating energy out of nothing. Okay? So you've heard about tidal waves, how tidal waves can be used to generate electricity. So if you don't believe in tidal waves because we don't see them, right? You say, where is the power coming from? But there are tidal waves, and this is the reality, so people try to harvest them. So don't dismiss this completely. Just be very careful in trying to understand what they're doing. You asked me a question one of you asked me a question about whether there was an error in the signs. Remember this problem that I talked about yesterday? This problem in which I have a wire that goes like this, right? I asked you to find the field here. I rechecked this. Everything should check fine. So what we said is correct, okay? All the signs agree. So what's in the notes is correct, okay? Because, but in going back to this problem, what we did yesterday, just want to say a few words. That's not our subject today. Just a few quick words. This kind of problem, we have a wire on which or through which a current goes like that. And the question was, find the B right here. Find the magnetic field at this point. We found out that this does not contribute, this does not contribute. Okay? So what contributes is this side, this arch, and this arch. They contribute, right? Okay, well, there's another class of problems in which I ask you to integrate the B field, the magnetic field, over this contour if there is a current source right here. So instead of the observation point, I'm putting a current source where the observation point is. Okay? What's the solution to this? I'm going to integrate B dot dl over this contour, the contour that is designated with the arrows. What is that? What would that be? Zero. Why? Because there's nothing inside of it. All right. Now, someone stopped during office hours. We had a busy office hours yesterday, and sometimes I have to apologize that I cannot address all your questions in the office hours. My apology in advance, because we have limited time. But someone showed up, and I cannot see where he is. The guy who showed up asking me about the proof that if I had any loop, this loop, for instance, this loop, as long as that loop does not include any current, the integration of the B along that contour is always zero. That guy is not here? Are you there? Okay. Do you know the easiest way to prove it? I gave you the hint right here. This is the hint to prove that always works. How? I divide this contour into arches and radial lines. Very similar to what we used to prove Ampere's law. So here, it's the same thing. I take radials like this. I'll take this away from here. I'll take radials like that. Please do not dismiss do not dismiss geometric interpretation. Do not. It's really powerful. It doesn't have to be fancy calculus all the time, fancy math. I did this division, okay? I divided this space over which the loop exists into these angles. And then I'm going to come and approximate the curve as arches, like this. Arches that have a constant radius with respect to the center. All of this will be arches. An arch, arch, go down, arch, go down, arch, go down, arch, and so forth. Okay? And if you want to close the loop completely, you have these radials that connect these arches. Okay? You're not responsible for these proofs, okay? But if you ask me, I will answer you. Okay? So you have radial, arch, 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 radial, and so forth. The integration, okay, going back to the problem that we started with, if we have this contour here, it's hard to see it since I covered it with the new structure here. If I had this contour contributes 0, right? This contribute. There's no contribution to this one. There's no contribution to this one. The integration along this contour is precisely equal to the integration along this contour. See? So if I have an I here, this I will give me a B which looks like this. Mu naught divided by 2 pi, 1 over r phi hat. Correct? Okay? So if I integrate this field from here to here, or precisely from here all the way to here, I will get a certain value. Does that value depend on r? No, because this has a constant r. So the arch, the infinitesimal area, infinitesimal length is d phi r. D phi, that's the infinitesimal length. That's it. So if I integrate this over this arch, this r cancels with this r. So I will get only the difference between these two angles. If I do the same thing here, guess what? I'll get the same thing, but in the opposite direction. So they cancel. So coming back to this one, for each arch here, for each arch on that away from the loop, or at the external side of the loop, there's another one which is closer to the source. So look, even though this is much farther than this one, the integration over this arch is the same as the integration over this arch, except the signs, right? One gives you positive, the other one gives you negative. So for each one outside, there's one close to the source, they cancel. So you'll end up with getting a 0, okay? That's a geometrical way to prove that, to prove Ampere law when there is no current inside the loop. All right. Okay, so today we're going to talk about induction, okay? Induction. Induction is the same subject as Faraday's law. So, how do we start this subject? It's a bit tricky. It's like the chicken and the egg. Which one do you like to start with? Some people don't like eggs. They prefer to start with the chicken. I happen to like both, the chicken and the egg. So it is really not a joke. It's really tough. Where do you start? When you have a physical phenomenon that is true, what do you mean by a physical phenomenon that is true, that is always happens? How do you explain it? Do you explain it from its consequences? Do you see that? It turns out that most phenomena are explained by their consequences. In other words, I cannot start from nothing and work my way to Faraday's law. I can't. Does that remind you of something? Coulomb's law? I did not start from nothing. I worked my way towards Coulomb's law. So I showed it to you and said, here, believe it or not, right? All right, so let's then, the best way to motivate the subject is we start with some observations, and some observations that are based on simple experiments. Observations that are based on simple experiments. So the first one, I'm going to take a flat wire like this, and I'm going to assume that I have a magnetic field that is going into the whiteboard, okay? So this is a conductor. Conductor, what's so special about conductors? They have free electrons. The electrons can move. So I have charges here. Now I'm going to move, pull, push, doesn't matter, move this bar in that direction. Okay, so there's a velocity in that direction. Now, if B is going inside and this E is moving in that direction, so I have a force. I have a force on that charge. The force is QV crossed with B. So QV is going in that direction. B is going in that direction. So I take QV, cross it with B. I will end up with a force pushing the charge up if it was positive, right? And if it was negative, it will be pushed where? Down. So I have negative charge. The negative will go, let's say, assume there's only one. The negative will go down and the positive will go up. Okay? So what is that? What is the magnitude of that force that we just that charge experienced? What is the magnitude of that force? It's right there. So the magnitude of that force, we're going to call it F sub B because it's due to the magnetic field. This is a model. Okay, this is a simple model, but it will be useful as you will see in a second. FB equals Q, the velocity, multiplied by B. Why? Because the two vectors have 90 degrees between them, so I'll end up with the magnitude of the velocity and the magnitude of B. Or if you like, you can do this. Okay? Assuming these are magnitudes. So now I have the accumulation of negative charges here. What will happen once I have the negative charges here and the positive charges here? I created an electric field, right? An electric field is created. What is the force due to the electric field that was created? The force that is due to the electric field is simply QE. Okay? Is QE. In which direction? In the opposite direction. If E is going in that direction, if B is going in that direction. If B pushed this down, if E is trying to take this and make it connect with the positive one. Simple, very simple experiment, thought experiment, right? Because we don't see electrons. And if you were to do this at home and try to take a voltmeter and connect this like that, you will get nothing, okay? So the people who did this experiment must have done something more to make them believe that this is the case. I'm being very frank with you.
Why do you have a velocity?
Why?
How is the velocity being generated?
The velocity?
We're moving the...
I had two horses pull this that way. I'm pulling it. Okay?
So we're pulling it out.
Yeah. Exactly. You happy with that? Just go with it for a little bit. No, nothing funny. There's a magnetic field here. There's a huge magnet. There's a huge one of those horseshoe magnets, very, very powerful. And I have a flat wire. It doesn't have to be flat, actually. You can have a wire. And, I mean, it is, I exaggerated this, but you can have, for instance, the way to do it, you can have a horseshoe magnet, suspend a wire from above, from the ceiling, with a tiny rope, tiny thread, and pull that thread slowly, okay? The key is you want to pull it with a constant velocity for now. If you pull it with a non-constant velocity, yes, a similar phenomena takes place. But right now, we're doing it with a constant velocity. All right, so we have this force equals the other one. So both forces must be equal. So we end up with QE equals QVB. Right? QE equals QVB. So now we're going to consider the voltage difference between this point and this point. Okay? I want to find the voltage difference between these 2 points. So the difference, the voltage difference between the top and the bottom, I'm not interested in the sign for now. It is the integration of E along the length of the wire. Correct? Guys, there's a lot of noise, please. This is being recorded, so anything can be picked up. Please. If you have any questions, let me know. So, guys, please. Delta V is the integration of E along the line. If I want to find the voltage between these 2 points, I'm going to trick you guys, okay? It's better to trick you right now and solve and give you the solution rather than trick you in the final exam, okay? So I want to find the voltage between these 2 endpoints of the wire. What do I do to find it? Let me put it this way. What do I need to find the voltage between these 2 points? Yes, please. Path integral. Okay. What was your assumption to do the path integral and to tell me that is the voltage between these 2 points? What was the assumption? I want to see big hands. Yes?
That was uniform electric field?
Or doesn't have to be to do the line integral. This is a review for the first part of the course. What was the assumption? Speak up. Go ahead. Nope. No, he said that. Not necessarily. I heard you saying something. Have the courage to speak loud. It's conservative, right? We assume the field is conservative. If the field is not conservative, what is the integration? What would the integration mean? I have no idea. Right? If the field is not conservative, don't talk about voltage. Drop the concept of a voltage if the field is not conservative. Okay? All right. So nobody asked me how long is this? Is this too long, too short? I want you, gents and ladies, to really be very sensitive to the importance of the difference, because this is the crux of our lecture today, the difference between electrostatics and electromagnetics. We really need to understand this firmly. Yes?
Is FE the force to the electric field?
Fe is the force that is due to the electric field.
And what's causing that?
Because right now I separated the 2 charges. There's an electric field, right? There's a lot of potential between the 2. Okay? They want to attract, but there's another force that is pushing them in the other direction. So we will get away with it. We'll cheat a little bit. We will cheat a little bit, and we'll say that I'm going to integrate between the two to get the voltage. Okay? Keep that in mind. It's a little bit of cheating. So if I do that, let's say this has a length of, I didn't draw the length of that line. The length is L. So this has a length of L. And right now I can say that delta V is L is L multiplied by E, correct? So E is VB. So this will be L VB. Do you like this equation or not? Yes? It's incredibly powerful because that's the start. This is the first time in this course that we link, guess what? The magnetic field to the electric field. Right? So this is not something that is a coincidence. It's not something random. It's the start of an incredible theory. Okay, but the key here is that the key here is that there's a voltage difference between the top and the bottom that is related to the magnetic field. If the velocity is 0, what will the voltage be? 0. We expect that. So what I meant by we expect that, if there's nothing happening, nothing is moving, I don't expect any interesting phenomena. Maybe I should have rephrased it like that. So now we have a voltage, a potential difference between two ends of this wire without putting a battery between them. Okay? Any questions on this? This is a very, very interesting thing. Okay? Now, I'm going to make things have another scenario. First of all, the key behind this interesting phenomenon is not just the magnetic field, not just the presence of the magnetic field, but the fact that Q is changing, is moving. Yes?
How did you initially separate the charges to create an electric field?
The fact that there's something pulling this with a constant velocity, okay? The fact that I have the electrons that are on this wire, they're free to move, right? Conductors have free electrons. The fact that I'm moving it with a constant velocity, I subject the electrons to that line, the first line above, F equals QV cross B. That will give me a magnetic force, okay? All right, so the next is I'm going to do is this. More interesting scenario. So I'm going to have a bar here, and just like this. This is a wire or 3 bars connected like that. And then I have a sliding bar, a bar that can slide easily, let's say 0 fraction, but it's touching the bottom wire here, okay? And I am moving this with a velocity, with a fixed velocity. Okay? So what is happening here? What is happening here is that I have, and then before I start asking myself what is happening, I have a magnetic field that is going again into this board. The magnetic field is uniform everywhere. Okay. This is where this argument of the chicken and the egg comes. Okay. In other words, how can I describe to you what's happening? Let's see if we can do that together. I move this with a constant velocity in that direction. The scenario here does not repeat itself precisely, meaning that there are charges on this bar. When I pull this in that direction, these charges will be subject to a magnetic force, correct? The magnetic force will be in the same direction. So there will be an E pushing, a force pushing the electrons down. But right now, they will not stop here. Do you see that? They will not stop because there's a loop. So the electrons can continue to flow. Right? So there's a current in it. So I'm deviating from the discussion in the book. Okay? Because the book tells you here's Faraday's law, deal with it. Okay? So I'm going to assume that I don't know Faraday's law yet. So we will have right now a current going through this. Everybody sees that? Yes?
Why is it pushing it left and right and not just up and down?
Okay. I have this is stationary and this is mobile. So this is sliding like that. Fair? With a constant velocity for now. Same argument, if I have electrons on this bar, they are moving. The electrons are moving. The electrons, to start with, the electrons on this bar are not moving. Okay? Why? Because I'm not pulling this or pushing it. So now when I pull this in that direction, these electrons will experience a force pushing them down. But now, because I created a loop, they're not going to stop. They're going to continue. Is that clear or not? Do you see? In other words, the electron will be pushed here. But why should it stop here? It can float. It's a conductor. So it's going to continue going around. So there will be a DC current. So I can come here and put a very, very tiny amp meter and find that there is a constant current going through that wire. Okay? So what have we done so far? What's the time? Where do we have a? Oh, there. I thought that my. So what have we done? We created a current based on what? Based on the movement of the bar. There's another way to look at it, is that I have a loop in which the net magnetic field that is piercing that loop is changing. See? Two ways to describe the same phenomenon. I have something which is moving, part of the loop is moving, or I have a loop expanding, which means that the magnetic field, that flux, that magnetic flux is the net magnetic field that pierces this loop, is increasing or decreasing. Remember I said earlier how important it is to sensitize ourselves to making these observations. And I said, I'm sure many people have seen it, because if someone comes up with something, guys, remember, other people are thinking of the same thing, most likely. Okay? Most likely someone else was thinking of the same thing. But the difference is that before Faraday came into the picture, people were not probably as sensitive as he was, or as patient. Because to observe these, it took him 9 years. Can you believe it? So it's not like he came to the lab one day and he saw something and he came up with a theory. No. Persistent. Every day he saw the same phenomenon, and he kept putting all this information together and then synthesized something new. Okay? So it's very important to be very patient and diligent when you see phenomenon. Okay? All right. So now I have a current in this. Everybody agrees? So for now, let's say the current is going in that direction. For now. We'll understand the direction of the current later on. Now this circuit, now I have a circuit, right? I have a circuit, I have a current in this loop. So I can represent this loop as a voltage source like this. I want to have a schematic for this, okay, a circuit schematic. So I have a voltage source and nothing like that. We all had circuits, correct? I can't do this. Why? Because the current here is what? Is infinite. So I have to cut this and put a resistor here. So this is equivalent to that. Yeah, question in the back? Please.
The current's going down, then how come the voltage is not that way? How's it going down?
Okay, I can switch this. I don't want to focus on the direction yet. I said that here, and I mean, this could be the opposite of this circuit, but it doesn't matter. So the current could be, I don't need to put even an arrow. Let's leave it like that. It could be up or could be down. We'll come to that. That's the direction of the current is established by Lenz's law. So it's something very fundamental. I'm going to come to it later. But right now, I don't want to give you this law and that law, and then you'll say, so what's the purpose of coming to school? You know, it's like a government. Just laws, right? That's Ottawa, not Waterloo, right? Okay, but I want you to see how we slowly, even if you were not heard, if you never heard of something called Faraday's law, you can come and do this observation and say, there's something really interesting here. And this is the first time I can connect the electric field to the magnetic field, which we never had before. Which means what? Which means that one causes the other. And the other must cause the first one. Which one starts it? That we will never know. But what we know is that one and the other are connected. Both are connected somehow. Okay? So our job in electromagnetic science and engineering is to really solve problems and demonstrate that how they are connected. How they're connected. Why they're connected, that's something beyond me. All right. So all you guys agree that this circuit can be represented schematically like that. Right? Yes?
How come let's say you have like a conductor and a wire, right? So how come the electrons in the wire on the left side will be forced downwards?
How come what? I'm sorry?
How come the electrons in the wire on the left side will be forced downwards?
This one here?
No, the one to the left. Over here. Yeah, over there.
This one?
Yeah.
Well, we start with this bar. This bar, I pulled it in that direction, right? So the electrons here will be forced to go in which direction? Down. Okay? So plus charges are going up, negative are going down.
So you're only moving the bar?
I'm only moving the bar.
Oh, I see.
Okay? If I don't move the bar, there's nothing happening in this circuit. Because if I don't move the bar, there's no forces to push the electrons. Clear?
The direction of the magnetic force acting on these electrons is constantly changing, right? Because the direction of its velocity is also changing.
Well, the velocity is not no. This direction here, okay, it is moving in that direction.
And this one.
And this one direction. So, good point. Let's see what that takes us to. So if I have electrons moving in that direction, okay, so QV, so QV is like this, crossed with inside, this, crossed with this. I have a force that moves them in which direction? In that direction. So they cannot move. Do you see that? So the electrons that are moving in this direction, they cannot jump out of this. They cannot.
Then how do they start moving to the left instead?
Well, I have electrons that I pushed here. Why should they stop here?
But the force is down.
Yeah, it forced them to go down. Now they find a path of least resistance. The electrons, if you push them, they don't like it. Nobody likes to be pushed, right? So if you push them here, they want to keep moving. So they find a smooth path to continue on. Guys, can we hear the question, please? Yes.
But wouldn't some charges be accumulated at the bottom of the bar?
No, none. Unlike that problem. That problem, there's nothing for the charges to move on to. This one, this is a conductor. So they keep moving like that. Okay? Now, Now, this means that right now, this is the schematic. This is the equivalence of this. This is the equivalence. So the question is, where do I put this voltage source? Where do I put this voltage source?
The rod, the moving rod is creating that voltage.
So he said, I put it on the moving rod. Who else want to volunteer? Where do I put that voltage? That voltage is mysterious, okay? That voltage is called EMF, electromotive force. Electromotive force. Motional electromotive force, okay? Motional because there is motion, okay? That voltage source cannot be isolated in location. We cannot, okay? This is a very, very confusing schematic that many people use in many books, okay? It's confusing because when I studied this the first time, I said, where in the world is this voltage? Well, they told me, you know what they told me? They said, assume this loop has a very, very, very tiny gap. That's what they told me. Assume that this loop has incredibly tiny gap and the voltage is right there in that little gap. But suppose I don't want to have a gap. There's no gap in this loop. I've seen many, by the way, graduate students struggle with this. If you understand it from the very beginning, you know, then you're really, then if one throws all kind of scenarios at you, you know how to address the more difficult scenarios. Okay? So, in summary, guys, where is this voltage? It's everywhere. Okay? So I cannot say that the voltage is here, 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 here. It is everywhere. How do we know it's everywhere? How do we know it's everywhere? We come and say this new voltage, okay, since it's a voltage, right? It's a voltage. This is a fancy way, script E. It has to be the integration of E all over the contour, all over the loop. So if we had an electrostatic scenario, the first part of this course, if I give you any loop, physical, non-physical, as long as it's a loop, meaning that it is a point, I go around, travel, and come back to that point. If I integrate E around that loop, what will I get? What will I get, guys? 0, right? Why? Because it's electrostatic field. It's conservative, right? Guess what's happening right now? We don't have 0, right? So if we don't have 0, so why are we talking about voltages here? That is really confusing. My objective for today's lecture is really to confuse you, okay? Once you get confused, either I see you on Monday or you come with interest, okay? Because we will address everything and provide a theory that satisfy everybody, okay? That really bring everything together. One more time before I move on, the electromotive force is the voltage in this mysterious circuit. What caused that voltage? What caused it? The change in the magnetic field, right? In other words, if the magnetic field, you see this loop here, there's a certain flux. Flux is the total magnetic field that is going through this loop. As I move this, that flux, that magnetic field going through the loop is changing. Is increasing in this case, isn't it? Is increasing. Okay? That causes this mysterious electromotive force, this mysterious voltage. Is there a specific place for the voltage in this circuit? No. Okay? Now, the implications, before I take your question, the implications are really interesting. Many people think of the capacitance and the inductance are analogous. One is similar to the other, except for differentiation. One you differentiate, one you integrate. No, they're completely different phenomena. The capacitance is an isolated property, of the circuit. An isolated, right there. There's a capacitance. Okay, inductance, no. Inductance is much more complex. Okay, so the inductors that we dealt with in our ECE circuit courses, everything is idealized. Inductance is a distributed phenomenon. Okay, capacitance is isolated. This will lead us to the concept of inductance. You had a question?
If you start moving at non-constant velocity, that's going to create AC current.
We're going to go to that. Yes. In other words, yes. In other words, if the velocity, if I have acceleration, then I have an I. That's very good observation. Then I have a V that is not constant. Okay, you see? You start looking at the phenomenon in its basic raw form, and you can anticipate what is to come. Right? In fact, I can guess that I can oscillate this back and forth with a frequency, right? So you train two horses to go back and forth with the bar, and you create an AC source, all right? What other observations are interesting to make here? What about the force? What about the force on this one? What is the net force on this bar? ECE105? Right? You guys had ECE105, right? What is the net force on that? Let's see how well you understand that subject. Thank you, because velocity is zero, right? Constant velocity, acceleration is zero. F equals ma. A is zero, net force is zero, but it's still moving with a constant velocity. So if the net force is zero, there must be the force that I'm pulling in that direction must be countered with a force that is pulling the bar in the opposite direction, right? The first one is the horse pulling it. The second one is a force, is a magnetic force, right? It has to balance that force, okay? So the net force has to be zero, right? The net force has to be zero.
Where is that? So it's coming from the magnetic field?
The magnetic field. Yes. Yes.
Well, you said magnetic force is moving downward.
I'm sorry?
Isn't the magnetic field a force moving down?
All right. So how do we end up with this magnetic field? This magnetic force. Yes.
The positive charge is moving up, and then we cross them with the magnetic field. The V upward, and then in, and then it goes that way.
Okay. Okay. Now, what I'm hiding from you is that the two phenomena are linked together. We isolated them to bring them together, okay? But we'll see later on, okay, we will see later on when, not too later on, but in the coming lectures that if I have a current that is moving in that direction, is going also to create a magnetic field, okay? So it's going to create a magnetic field that will imbalance, that will offset the balance that we have here. We'll leave that till later. All right. So now I'm going to talk about flux, okay? So flux, I'm going to use the definition of flux to help us develop the theory in a more complete fashion, okay? So that's what I'm going to do next. I'll try to finish it in 6 minutes here. Okay? So if I have a loop like this, I have a loop and I have a B crossing it. Okay, this is a magnetic field crossing a rectangular loop. So it has a length L and a side A with depth L. Okay. Looking from the side, so let's say that this direction is X, this direction is Y, X, Y, and that direction is Z. So here, for this scenario that I drew, B is in the Z direction, Y is along the A, the dimension A or the length A is along the Y direction, and L is along the X direction. Now I'm going to view this from I'm going to view it looking at the ZY plane. Okay, so this is the ZY plane, so the loop will be like this. Okay, so I only see one side. Okay, I'll see the A side. All right, so the B is going in that direction. Maximum B will be cutting through the loop if the loop was orthogonal to the direction of B. So the total, the flux, magnetic flux, is defined to be the entire B that goes through a surface. So this is a surface. The magnetic flux that's going through the surface, you integrate B, you integrate it over the area. Okay? You integrate it over the area. Remember, the area has a vector. Okay? So you take the area vector, which is pointing in this direction like that. You take B dotted with ds. For this particular scenario, you will get B multiplied by the area of that loop, which is L multiplied by A. Okay? So that's the total flux that is going through the loop. Next, I'm going to bend this loop. Okay? So it's going to be like this. So again, I'm still looking into the ZY plane. I'm still looking into the ZY plane, but I tilted this loop. Now the flux, the magnetic field is still going in the Z direction. So my question is, how much flux is going to go through that loop? How much flux? So let's say this length is A, correct? And let's say this angle is phi. So the flux that is going through this loop is A multiplied by cosine phi. So the entire flux, so this is scenario 1. So this is scenario 1 here. Scenario 2, the entire flux for scenario 2 is the integration of B. B is in that direction. A, or ds, is in this direction. Right? Because I tilted the surface. The vector of the surface is always perpendicular to the surface itself. Well, this is an easy math. Why? Because this is a rectangular loop. So I'll end up with the area of the loop, okay, B, L, but not A cosine theta. A cosine theta. Well, in the extreme scenario, so scenario number 3, the loop is flat like that. So this is my loop, scenario 1, scenario 2, scenario 3. So this is scenario 3, scenario 2. The B is going in this direction, obviously for scenario 3. ds is going in that direction. ds crossed with B is 0. Sorry, ds dotted with B is 0. So I'll end up with 0. Okay? So the flux is changing as my loop is is changing its orientation, right? This is going to help us actually create the concept or develop the concept of an AC motor. We developed the concept of the DC motor, but this will help us develop the concept of the AC motor. So if I take a loop just to prepare us, anticipate what's going to come in the next lecture, if I have a loop like this, and if I start bending it, just half a second, half a minute. If I start bending it like this, what will happen to the flux that is going through it? It will be changing. So I expect to create a current in that loop. All right, guys. I'll see you next Monday. Have a good weekend.